So we've claimed that eigenvectors of a symmetric matrix tell you a lot about some deeper information about the matrix. So for example, with data, which is our focus here, the eigenvectors of the covariance matrix give you an orthogonal set of axes onto which, if you project the data set, you get a decreasing ranked order of variance along those axes, or at least this was the claim, something along those lines from last lecture. And in this lecture, we're going to see how that works, if it's true, how do you show it mathematically, and how are we going to make use of this going forward. All right, let's get started. We're going to be doing a fair amount of work with some vectors, so I thought it would be useful to start with just a reminder of a particular rule that we saw before. So this should be a reminder, but you never know how much you might have remembered from the last lecture, so we'll just write it again. So suppose you have two different vectors, A and B, and you try to look at their dot product. Now, the dot product, as you might remember, is sometimes, I think in terms of dot products, that's more commonly used, I think, in the science, in physics, or like in the physical sciences. But if you think in terms of matrices only or so, then you write this as the transpose of the column vector A times the column vector B as a matrix product. So you could write it either way, but I think of it, I have this sort of geometric picture in my mind all the time when I write it. And the geometric picture is the following, that the value you get when you compute this dot product, or this transpose, whatever, is the length of the vector B, the magnitude of the vector B, times the magnitude of the vector A, times the cosine of the smallest angle between the two vectors. And so let's just draw an example of two vectors. So let's say this one is B, and let's say that this vector here is A. Right? Now the angle between the vectors always means the smallest angle between the vectors, and so that's here, so that's theta. And if you want to, what I want to look at is, I want you to pay attention to this term here, A times cosine theta. So let's suppose we create a right triangle like this, right? So that's a 90-degree angle where I put that little box shape. Then the hypotenuse of that right triangle is the length of the vector A. And A times cosine theta is this length here. Right? Now that is sort of as if, imagine if you sort of like shined a light on the vector A here, it would cast a shadow along the vector B that long. And so that's called the projection of the vector A onto the vector B. Right? So that's the name for that. And so we write that, you can write this expression for the dot product, you can write this as the length of the vector B times the projection of A onto B. And of course, that projection doesn't depend on the length of the vector B. So if B is not too long, you kind of extend it out. So if B was just like a short vector here like that, say, then the projection still happens just along this line. The line extends all, infinitely along in the direction of the vector B. Okay, so the reason I mention this is that sometimes you have two vectors and all you care about is finding the projection of one onto the other. You want to find out sort of what amount of its length comes from a length in the direction of the other vector. And so the way you do that is using this formula, but kind of getting rid of this piece here. And the way you do that is you turn this thing into a unit vector, because then the thing that appears here is the magnitude of that unit vector, which is 1. The magnitude of unit vectors is 1. So the rule then that I wanted to draw attention to today is this: A dotted with B hat, where B hat is a vector of length 1 in the direction of B. So in other words, the vector B can be written as its magnitude or its length times the unit vector in the direction B, B hat. Okay? So this thing here, this dot product just gives you the projection of A onto B. Oops. Because the thing in front would be the magnitude of the unit vector B hat, which is 1. And so this is a pretty important rule. I would probably, highlight it or box it or something like that in my notes, because it's really important and we'll make use of it a bunch today. This geometric picture is very handy. It's useful even when you're dealing with problems in high dimensional spaces, because the geometric picture still kind of holds. All right. So now let's get on to the principal component analysis details that we want to look at. So we want to really dig into the mathematics and see why some of the most important, why some of the most useful aspects of PCA are actually true. So these are some details. And this is the focus of today's lecture. Principal component analysis as a whole is the focus of the class for, I think, the next 2 weeks, maybe even one lecture past that. It's really one of the main tools that we'll teach you in this module, principal component analysis. And it's super useful for understanding the other tools that we'll see as well. So it's definitely worth spending time seeing the mathematical details and understanding them and working through them to make sure you believe in the kind of claims that come along with principal component analysis. Okay, now, so I want to start out just by saying, consider you have some data matrix, and I want to look at just one observation from that data matrix, or rather one row. Okay, so consider, and let's give it a name. We'll call it observation number K. Observation number K. And to make my life easier, I'm going to say for centered data. And the centered data is the usual notation. We'll call that matrix X, but I want to highlight this centered because it's important. So observation K, then, we'll often write that as this guy, lowercase x sub k, with a vector symbol over it. So this is a row, it's row K of the matrix X. It's meant to be the capital X as a column vector. All right, so you take that row out of the matrix X and turn it over so that it's a column, and that column vector is X sub K, right? Now let's draw a picture of kind of where does this observation live in sort of data space or observation space. So to make our lives further easier, let's look at the two-dimensional case, or the bivariate case, two-variate case. This just helps us to draw things. So the bivariate case, let's draw in black. I'm going to put the axes of the original data matrix, like this, because when we do principal component analysis, we're going to transform the data onto some other axes. So these are the axes for the original X, right? So these might be like height and weight, for example. I think that's what we talked about in the previous lecture. Now let's just put in blue here observation K, right? So it points off somewhere like that. It lands at this spot, say here. And we can express that. I mean, so that is written in the language of this space, right? So we can write this as, how much does it move along the horizontal axis? Well, that's stored in X, row K, column 1. And how much does it move along the vertical axis? That's stored in X, row K, column 2, right? And so this thing is a column vector, so this is this guy, right? And you can write that in the following. It looks sort of clumsy, but you could write it if you wanted to as that first number, X sub K1, right? That's the projection of the vector xk onto, now I need some unit vector in the direction of the horizontal axis. And so I'm going to put this here, and I'm going to call this I hat. That's a common name for horizontal unit vectors. Like that. Right? So that first number, x sub k1, is xk dotted with I hat. It sort of seems silly to write it out in such a long way like that, but you could do that. And similarly, we could introduce a unit vector here and call this j hat. And then this guy here is that number x sub k2 is the dot product of xk and j hat. Right? So that's a sort of a long-winded way to express sort of what is the kind of, we might call like the address of observation K on the original axes. Right, the axes that the data matrix X kind of came with natively, right? Now, when we do principal component analysis, what we do is we transform, or we make new axes, all right? So in PCA, in principal component analysis, what we do is we transform X into some new matrix that I'll call Y. And the rows of Y, or the observations of Y, are the rows of X, but described on some new axes. So described, or maybe you should say addressed, I don't know, on these new, what we call principal component axes. Principal component axes. Now, transforming onto a new set of axes doesn't make the other axes the principal component axes. What makes them the principal component axes is that we choose them in order of greatest variation, of greatest variance, right? In the way that we discussed in the last lecture. But so let's draw a picture and make sure that we understand that, or at least understand what this new. I don't think I need all this stuff. I'm just going to take this much, and we'll get rid of some of it. So let's see what these new axes look like. Right, we'll oops. Now, so I'm going to erase the old address. But we can leave the original axes on there. I should probably, yeah, let's copy that just as a reminder for us. Right. And so what we do with the principal component axes is there are some new axes, and I'm going to draw them in brown. It looks something like this. And they're perpendicular, they're orthogonal to each other. Let me move this J. That's kind of in the way. Put that over there. Like that. So these are meant to be orthogonal. I didn't really do that perfectly. But we call these like principal component 1, and this guy's called principal component 2, right? And we will want some unit vectors in their direction, and so I'm going to invent them now. So one points like that, and we'll call that guy alpha hat 1. So alpha is just the symbol we're going to use. The hat means it's a unit vector, and the 1 means it points along the direction of principal component 1. And so the unit vector along there is called alpha hat 2. Right? It's just its name. Now, the point of the data, and remember these things share the same origin because we're using the centered data. Like, that just sort of saves me. You can do this without centered data, but you have to add a step. That step doesn't really change any of the important rules and theorems that we're going to find in any significant way at all. So it's fine just to think of it as already being centered. But sometimes you have to do that. Depending on the algorithm you use, sometimes you have to manually center the data first. Other times it'll center it for you. You have to kind of pay attention to what are the rules of the code that you're using, or so on. Anyways, so what is the address of this point in the principal component space, right? Well, it's, again, the rows of the matrix Y, and so they look like this. So Y sub k1 and Y sub k2, right? So this is row k of the matrix Y written as a column vector, and the lengths here, those values, Y sub k1 and so on, these are the vector x k dotted with alpha hat 1. And Y sub k2 is the vector xk dotted with alpha hat 2. Right? So it's the projection onto principal component 1 and the projection onto principal component 2. Right? So that's what those things are. And so this is, you could call this the address of observation K in principal component space, or on principal component axes. Right? So I think this geometric picture is helpful, to me at least. And just as a reminder, so these brown things are the principal component axes. It's an axes. Like that. Okay. Now, so if let's kind of take a look at what does the two matrices X and Y actually look like. So, right, so the matrix X looks like this. It's a bunch of rows. Row 1 is x1 dotted with I hat, and then x2, oh sorry, that should be x1 dotted with j hat, right? So there's two elements to it because this is a two-dimensional case. And then that's one row, and then you keep on going down. And the last row is xn, if you have n observations total, dotted with I hat, and then xn dotted with j hat. Right, so that's what the matrix X looks like. And sometimes I like to use this sort of silly notation, or this drawing tool for myself, to say, look, what this is x1 vector, which is a column vector, and so I transpose it to make it a row vector, and it takes a shape like this. Right, so I do that. I don't know if this is not a very standard notation, but or tool, but I like this. I find this useful. And so there's one more here, and then one more here, and all the way down dot dot dot, right, until you get to the last one, and that's n. Right. So that's how the matrix X looks, and the matrix Y is pretty similar to that. So let's move this over a little bit. copy it. Right, oops. So the matrix Y looks really similar to this, but what's different is the unit vectors are different. That's pretty much it. Right, so let's fill this in. So this is the matrix Y. We're still taking the dot product of the observations that you could label as x1 and x2 and so on. So we can leave those x's there. But what's different here is this is not I hat and that's not j. Oh, those are supposed to be hatted. Sorry. But instead, those are alpha 1 and alpha 2. This is just a repeat of what we saw above. And the reason I'm writing this out is that I want to understand, how do I actually produce this matrix? Right? So how do I make the matrix Y out of the matrix X? Right? So here let's write down how the transformation works. Right? Transformation. Now this is a key kind of equation that we're going to use repeatedly. So the matrix Y is equal to the matrix X times some other matrix. And just for convention, due to some convention, we call this matrix A transpose. It's sometimes useful to call the matrix, to save the name A for a different matrix. Maybe it'll see why in a second here. All right, so but this is an important kind of general layout that we want to have. So this tells us, how do you get from the matrix X to the matrix Y? Well, you multiply it by this matrix A. Well, what should that matrix actually be? Right? So here's how the transformation looks. So we have the matrix Y on the left-hand side. I'll just write that like this. Y1 transpose, like a horizontal guy. That's a row. Dun, dun, dun. And then Yn, that's row n, right? And you get that by doing the following thing. You take the matrix X, X1 transpose as a row. And there's the last one. All right, so that's matrix X. Now I want to put a matrix here that when I do the matrix multiplication, I'm going to get these guys. Right? So you should think about what should go in that matrix. And here it is. So it's alpha 1 hat as a column, and alpha 2 hat as a column. And that's it. It's a two-dimensional, bivariate case. Right? Because to make this row here, you take this guy here, move it over here, line it up, do your dot product, and that gives you the first element, right? To get to the well, yeah, I hope it's clear. So if you look at that thing and sort of think through, how does the matrix multiplication work, you should be able to see that this would do it, right? This layout here. Oh, and just some terminology here. We're going to be encountering this. There's a lot of terminology that gets kind of thrown around, and not everybody uses it the same way. So this is this is an inherent frustration kind of in all of, really in life, I guess. But it seems like it's particularly strong, I find, in statistics, or maybe it's just in things that have the kind of the right age as statistics as a science. But so this thing, row K, column J of the matrix Y is called, this is just a name, and you can ignore it if you don't like it, but this is called the j'th score. Let me rewrite that, because that's kind of the whole point here, is that word, the score. Of observation K. All right, so this is just some lingo, some language or terminology that people use. All right, but so that's where the term score comes from. You'll hear scores. What are the scores? Show me the scores, or something like. You'll hear people say stuff like that. Right. So if this matrix here is A transpose, right? We should be able to write out what is A. Right? I hope you can see that relatively quickly. So if A transpose looks like, I'll just grab it. Looks like that. Then the matrix A has the vectors, the alpha vectors as rows. And I guess you want to put these as transpose. You write it as transpose. Right? You kind of don't need the transpose if you write the horizontal lines telling you this, look, make this thing sideways. And then alpha hat transpose 2. Right? And this matrix, the matrix A, just more lingo. This is the only 2 weird terms I think we're going to introduce today. I think. This is called the matrix of loadings. I'm not sure where this word, like these names, scores and the loadings and the scores. So that's the key word here. And this is just more lingo. This must come from some picture that I'm not really aware of, but the idea to me is that you think of, I guess you think of this thing, this is one of the loadings. It hits this thing, and then the element that you produce over here, the first top left element there, that's the score that you got when you loaded, when you use that loading on the matrix X. I'm not sure where this terminology comes from, but you can try to make it work for yourself there. Okay, so this is the structure of how, so if you know if you have this geometric picture of the principal component axes as this turned thing, now we see how you make unit vectors along them, and then you can see how do you generate the matrix Y from the matrix X, or the centered one at least. Now, what's important about principal component axes is kind of exactly which alphas should we choose, right? And so I'm going to make so the rest of today's lecture is about 2 really important claims that tell us the most important kind of powers or uses of principal component analyses. And so we're going to prove them. And so let's go ahead and say this is claim number 1. And I don't think this is an obvious thing, so you might want to call it like surprise number 1. If you're a mathematician, just call this theorem 1. I should make this red, I think. Okay, and so the claim is the following, and then we'll go ahead and prove it. It's nice. If we take out the columns of the matrix Y, and we haven't done that yet, but let's say I want to. So like the observations in Y are the rows. And so I want to strip out the columns. So let's call that capital Y with a vector sub k. I don't know if that notation is used in any of the books or not, but let's do it. Let's say that this capital Y sub k is column k. So it's important. It's stripping out the columns of the matrix Y. Right? Then the variance down that column the variance of yk, right? So you just take the variance of all those elements, turns out to be equal to the following. So it's alpha transpose k times the covariance matrix of the matrix X, which we'll write as sigma, right? Times, and I'll write that in a second, I'll define it, alpha k. Right, now this is a surprise. It's not something, I don't think you should have, I think I might have told you this in the last lecture, but I think this is sort of a surprise that the variances of those columns of the y of the PCs, so the variance along principal component 1, is this weird multiplication, alpha 1 transpose times the covariance matrix times alpha 1. And so again, sigma here is the covariance matrix of x, or for x. Right, so in other words, sigma, I think we were calling this capital S before, as a hint that it was going to become sigma, 1 over n minus 1, so it's the sample covariance matrix for x, x-centered transpose times x-centered. I'll put the centered back there so you remember that that's part of the definition of the covariance matrix. Okay, so this is an important result because we use the variance as our guide for which directions should we put these principal components, right? We want to put them in kind of ranked order of most variation. And so being able to express that variation in a simple way, which we've just done with this thing, is important. So let's see how do you prove this thing. It's relatively easy. All right, so here's the proof, right? So let's suppose I'm going to introduce some notation to make this work. So let's say we make the covariance matrix for y. Let's call that sigma with a subscript of y kind of trailing behind it. So if this is the covariance matrix for y, right? So in other words, sigma y is equal to 1 over n minus 1 y-centered transpose y-centered, like that. Right, so the same definition as for x, except with the matrix y in there. Well, then the variances of y are in that, right? Because this is what the covariance matrix is. So the variant, remember, the diagonal elements are the covariances, because remember, technically the name is the variance covariance matrix. So the diagonal elements are the variances, and the off-diagonal elements are the covariances. So then the variance of column K is equal to the kth diagonal element of that matrix. So row K, column K of Y's covariance matrix, right? So now, since what we're trying to prove is this thing here, right? We're going to start from here. And so we're going to use, so what we want to do now is just rearrange the right-hand side, right? So express this guy in terms of x. Right? And to do that, you use the following transformation. So we had this transformation, like y is equal to x times a transpose, right? It turns out this is also, so the centered thing is exactly the same transformation. You should be able to show that by yourself. It's you can do it in a few lines. You should try that. It's a good test to see if you are following along. So this is how you make the centered y out of the centered x, right? That means then that sigma y is equal to the following. So it's 1 over n minus 1. Right, so I'm just looking at this thing here and substituting in. Right, so the first thing is the transpose of y, of centered y. So that looks like this. This quantity transposed, and then times the matrix y. So that's xc a transposed. Right? Now we do that transpose on the left, And remember that the transpose of a product of matrices is the product of their transposes, but with the order flipped. Right, so this is 1 over n minus 1. So this is a rule for linear algebra that you may have only heard for the first time in the last week's lectures, but you should know it. And so this looks like this. Right, so that's the transpose of this guy. Right. And the other thing I'll just leave as it is, and I don't need its parentheses for any reason, so I'll take those off. Like that. And now you can do this matrix multiplication. You can do the inner multiplication first. Right, so let's move the constant inside. So what we have is A, 1 over n minus 1, xc transpose, xc, A transpose. Like that, right? That thing in parentheses should look familiar, right? That's the covariance matrix for the matrix X. Right? Now, all we have to do to kind of finish our job, to finish our proof, is to understand. So if that's so we've really done most of the work. So this matrix here is given by that. And the variances are the diagonal elements of that. So we have to kind of understand what are those diagonal elements. Okay, so how do we write this? So we write this as, let's just write out the using my sort of line notation. So this is like alpha 1 hat transpose as a row. So I'm writing out the matrix A, and then dot dot dot, and then alpha n hat transpose. So now I'm not doing the two-dimensional case. Okay, I'm doing the n for the multivariate case. Then times the matrix sigma, which I'm not going to expand, and then times alpha A transpose, which looks like this, right? So it's alpha 1 hat as a column, dot dot dot, and then alpha hat n as a column. Right? Now we can distribute the sigma. We can do that multiplication first. So this guy comes down just as is. And we get sigma times this vector. So that's the first column, if you wish, sigma times that vector. And then the second column is sigma times alpha hat 2, and so on. And then the last column is sigma times alpha hat n as a column vector. Right? So each one, I hope that's clear what I'm doing there. Each one of those columns is made from a matrix multiplication of the matrix sigma and the column vector alpha hat 1, 2, 3, or whatever, and up to n. Right? So then, what does this tell me about the diagonal elements? All right? So what is, for that this thing on the left-hand side, that's sigma y, right? What is row k, column k of that thing, right? So you have to think about this. So row 1, column 1 is made by taking this guy, turning it sideways, and doing a dot product with this. Right? So that would be, I'll just write it here, alpha 1 hat transposed times this guy. Right? But there, so this actually tells me the rule for row k, column k. I just did 1 there because we could draw it. And that's the proof we were after. Right? So that proves that the variances, so let's go back and see why did we bother with this. Right? This is important because principal component analysis is focused on the variances, and the variances on the PCA axes are given by these guys here. Right? So you take the unit vectors. Oh, those should have been unit vectors. The alpha hats. Right? And you multiply them with the covariance matrix X in that way. And that'll tell you the variance along You know, if you take unit vector number 2, it'll tell you the variance along axis 2, and so on. Okay, so that's useful, I think. Okay, now the next thing, in order to do I'm going to do one more claim, and it's the more powerful one, I think. But in order to do it, I need to introduce some notation. Right? So we're going to talk about the eigenvectors and eigenvalues of the covariance matrix. But I need to introduce a convention for not only how I name them, like what letters I use, but how do I order them? Like, you know, there's going to be like 6 or 7 or whatever number of eigenvectors. How do I choose the ordering of them? Which one do I declare as eigenvector number 1, and so on? And so I'm going to introduce some notation for that, and a convention. So eigenvector eigenvectors and values of sigma. So this is sort of notation and convention. Notation and ranking. Or ordering. You should probably call it ordering. It's a better. Rank makes me think of matrix rank. Ordering convention. Right, so we really just need to introduce some symbols to name them and then tell how we ordered them. Okay, so let's say let the eigenvectors be the unit ones, u hat I. Right, so we'll say that is, let these guys be unit eigenvectors. Of the matrix sigma, the covariance matrix for X, right? And so what that means, of course, is that the covariance matrix times this guy doesn't actually change the direction. The output vector that you get is the same as the original one, but just stretched or shrunken depending on the eigenvalue. So it's a constant, lambda I, that we call the eigenvalue, times u hat I. Right, so that's, this guy is the eigenvalue for this particular eigenvector. Right, so you get a different one for each eigenvector that you use, or you might. Okay, now we make use of the fact that sigma is symmetric. So since sigma is symmetric, we have the following special rule. So the UIs are orthogonal. I think we talked about this several times now. In fact, they're called orthonormal because they're perpendicular to each other and they all have length 1. So in other words, u hat I dotted with u hat j can be only two things. It's either 1 if I and j are the same, or it's 0 if they're not. Right, so u hat 2 is perpendicular to u hat 4, 5, 6, and whatever. But u hat 2 has length 1. Okay, so that's the symbols. And the ordering, so like what is the meaning? U hat 2, how do I sort out the ordering, right? So we're going to choose the ordering. In the following way. So such that the ordering of I, such that the following is true. So if I is less than j, so in other words, this is telling me where do I put for u hat 1, right? Well, that means that the magnitude of eigenvalue, the absolute value of eigenvector I is bigger than the absolute value of eigenvector j, right? So the i's are put in order of decreasing absolute value of eigenvalue. All right? Hope that makes sense. Okay. And this is important for us because, well, hang on. No, we haven't seen this yet. So yeah. Sorry, getting ahead of myself. Okay, so now let's look at claim number 2, which is our last thing for the lecture. Its proof is a little harder, but it's more important, I think. Claim number 2. I don't know what these should have names for theorems or something. Claim number 2. And again, this isn't something, sometimes with linear algebra or with statistics or whatever, so you find out something is true, and then it seems like, well, yeah, of course it was true. Like, absolutely. Like, of course the Earth is round. But for so long before you forget, like, people didn't know, or what, I don't know. So it seems like it should have been obvious. But maybe the Earth being round was kind of obvious. I don't know. It's not obvious if you don't get to go far away from it or travel long distances. Okay, so anyways, so claim number 2, or so-called surprise number 2, because it is kind of a surprise. And again, if you're a mathematician, just call it theorem number 2. Is the following. Okay. The alphas which maximize the variances, right? So we choose the principal component directions. That tells me what the alphas are. So the ones that give the largest variances, so which maximize I'll spell it in my American spelling. The variances. Each of these guys are equal to, and the variances look like this, right? So this is, we saw this. That was proof number 1, or claim number 1. And these should be hats, right? So the alphas that maximize this formula, it turns out, are the eigenvectors of the covariance matrix. So that's a pretty big deal, right? So these UIs, remember, are the eigenvectors of the covariance matrix for X. So those are the directions that we should use for the principal component axes. So I think I said so in the last lecture, but I certainly didn't prove why. I just sort of argued for it. Or I think I called it a spoiler. And then there should be dramatic music. I should make these videos more fun. I should put like some funny like noises and music and stuff like that. One day. Okay, so and what are those variances? Well, we can calculate them really quickly right here. What does the variance of yk look like if that's true, which it is true, and we'll show it. Well, okay, so you put in the u's. Oops. The variance of yk is u hat k transpose times sigma times u hat k, right? So that's just calling the alphas u. But those guys, right, u's are the eigenvectors of the matrix sigma, right? So sigma times u gives me the eigenvalue times u, right? So this guy here is really just the eigenvalue times u. So I have u hat transpose times k, lambda k, u hat k. And lambda is just a scalar. It's not a matrix. So I can pull that out to the left here. And what I have then is u hat k transpose times u hat k, which is also called u hat k dotted with itself. Right? And we said these unit vectors have length 1, and so therefore these are lambda k. So that's pretty cool. So it says that the variances are actually the eigenvalues. So this is the origin of us using that ordering. So we put the largest variation happens where there's the largest eigenvalue. And so that we call PC1. And the next largest we call PC2, and so on. So that's where this ordering comes from. So this is such an important result, all these things put together, that I'm going to write them out in kind of words. This is maybe, I think the purpose of today's lecture is seeing why these things are so, and so that in such a way that you can really completely understand it, I hope, and kind of own it. But if you can't, at the very least, you should know what it is that we've seen. And so let's see what that is. So the key point of today's lecture, apart from the deep understanding, is just to know the following things. So the unit eigenvectors u hat I of sigma, defined by this relationship, with I in order of decreasing lambda, it points along the direction, is along the ith PC axis, principal component axis. And the variance along that axis of the data along that axis, and lambda I is the variance of the data along that axis. Oops, I'm getting my handwriting's getting a little messier and messier as the lecture goes on. Axis, geez. Okay, so that's an important enough result that I'm going to put it in a box here. And again, the real purpose, I think, of today's lecture is for you to know this, but also to understand why it's true, right? So this is like the key point of today's lecture, this boxed statement. I said it in the previous lecture, but we didn't actually prove it, and we are one step away from proving it. And this last proof, which is a proof of what we just saw, claim number 2, okay? This is a little trickier, right? But we can do it, and you can do it. I think you all have the powers to do it. Proof. And it's worth doing because this is such a powerful result, all right? So principal component analysis is this really important tool. And this is its most, kind of, I don't know, this is the most important thing about understanding how it actually works. Okay, so here's the proof, right? I mean, if you want an intuition, right? You remember I talked about these other things in physics, like the inertia tensor and its eigenvalues and eigenvectors. Like the eigenvectors tell you something about how difficult it is to rotate an object. It's some physical principle thing. It's nothing to do with statistics. Well, in statistics, the covariance matrix tells you something about the variation of the data along the principal component axes, and the eigenvectors are the direction of the principal. So I think it tells you something about how difficult it is to vary the data in a particular direction. So I think it's important to understand that this is really true. Okay, so the idea is what we want to do, the claim, let's go back, it's been a while, right? So the claim is we want to, that the eigenvectors of sigma actually give us the greatest variation, or the variances, right? So what we want to do is we want to maximize this expression here, right? Alpha hat t k, these are the variances. Right, so we want to maximize that. That's from claim 1. Right? So if you want to do that, that's the same as a different maximization. This is some like deep, clever trick. Same as maximizing a different thing. And this is a you should write like, what? This is some crazy cool trick. it's the same as maximizing the following thing. Some function of alpha hat plus a new variable that I'll call gamma. And this thing looks like the original expression, so I'll just steal it, plus something new, or minus, I think, minus gamma times, I think it doesn't matter if you use gamma here, or a plus or a minus, minus alpha hat k dotted with alpha hat k minus 1. So how is that the same? That maximizing this is the same as maximizing just that first term? Well, it's pretty it's ingenious. It's the same because, I mean, it seems kind of, it's so ingenious it seems stupid. Because this is 1, right? And so this whole quantity is 1, or 0. So this is the same as maximizing. This is the original thing, and then minus some weird version of 0, right? So this is a super powerful, clever, and bizarrely constructed trick. So this is a cool trick. Cool trick, and it's an optimization trick. Gamma is called a Lagrange multiplier, named after a person. Right, I think the textbooks tell you that this trick is used, but they don't really say much more, and they just kind of leave it with this deep-sounding weird name, and then you run away. But you can look at how the trick works. It's simple. It's weird, but it's simple. Right, so let's do it. All right, so here's the, to make this work, you do the following. Okay, so let's say we introduce this notation. So alpha hat k has components that look like this. So if you make a row vector by taking a transpose, it looks like this. Alpha hat, and I'll call this k1. And then alpha hat k2. You don't really need commas in here, but, and so on. Up to the last one, alpha hat kn. Right? So that's just naming the notation of the components of the alpha hat vector. And I'm going to introduce some derivatives. This notation, so the partial derivative with respect to alpha hat kl is just going to be given by this notation here, right? Then the maximum happens, or the maximum of f is where, how do we write this? The derivative with respect to L, each of these derivatives of f has to be 0. It's also true that the derivative of f with respect to gamma has to be 0. And that's kind of, sometimes that gives you new information. In this case, it just gives you back the restriction that the alphas have to have length 1, which we've already enforced or demanded, really, just from the notation. Okay, so then the maximum of f is where that happens. Okay, and so in order to do those derivatives, like here f, so this is one of these annoying things. Here f is written as this giant like matrix multiplication thing, but in order to maximize it, I have to take derivatives with respect to like the individual components of these guys. And so in order to do that, I have to re-express this thing in terms of all the components of these guys. And that's why it really makes kind of a mess, but I'll show you the result. And you can play around with it and see if you can show it. So f can be rewritten like this, okay? And now here's the super annoying thing. I don't know why this has happened, but statisticians have taken over the symbol sigma, which is usually used for a sum, and they're now using it for this matrix. Fine. The problem is we got some sums around too. And so this formula has both sigma as a sum and sigma as a matrix. So I'll try to indicate them by drawing the sum sigmas a little weird. So there's a sum sigma, right? It's a sum over the index I, and there's a sum over the index j. And I hope it's clear from context what is the range of these sums of alpha hat ki, and then row I, column j of the matrix sigma, all right? That's not a sum, times alpha hat kj minus gamma and another sum. Probably should use a different letter here than I, so you don't get it mixed up with the earlier one. Alpha hat ki, alpha hat ki minus 1. All right, so that's what f looks like if you write it as a, you fully expose the coefficient, the components of the alpha vectors, so that you write it as a sum, so you can see the matrix multiplications written out completely. So f looks like that, and then therefore, and further, the derivatives look like this. And you can check this too, you should. It's the matrix sigma, and so this is now, I'm doing the derivatives and then putting it back into this compact matrix multiplication form. Alpha hat L minus gamma alpha hat L. Right, so that's what those derivatives look like. Okay, so he says, so what does this mean? What does this tell me? Right, so when is this maximized? Right, it's maximized when these derivatives are 0. So what does that mean? So the maximum is when that thing on the right hand side is 0. And so let's just take it. This is a difference. And so we want that difference we want these two things to be the same. Right? But now look at that equation for a while. That's the covariance matrix multiplying a vector, and it gives you back a constant times the same vector. So those are special vectors, right? So which means the alphas are the eigenvectors of sigma, which was what we were trying to prove. Which I think is pretty cool. So I'll grant it that second proof is a little tough. Maybe some of you are not so happy to see this appear, and this is horrible. I don't know how to. I feel like I need to apologize to you for generations of statisticians who think that this is just acceptable behavior. I mean, what are they going to do? Next thing you know, the number 7 is going to be a variable. Like, come on, there's certain symbols. It's like, what are you going to make plus a variable now? Ugh. Anyways, so okay, this proof is a little bit messy, and I've skipped steps that are kind of important, right? Like I claimed that this thing can be written like this, and that is, you have to take some work to show that, and then I've claimed that those derivatives turn out to be that. But so if you just show those two things, you'll be home free. I hope you have a little bit of a better feeling for the principal component analysis mathematical details now, and are ready to dive in and start doing some examples with some code, which is what we'll do next time. I'll see you then.